So second lecture out of these lecture over the reactions of alkenes. So we'll just look at more reactions in this lecture. So if you take a alkene and react it with Br2, or it could be Cl2, and not F2 because F2 is too reactive, and generally not I2 because it's not reactive enough. So what happens if you take an alkene and Br2? Then we're going to take these two electrons, make a bond to bromine, and we're going to kick a bromine off, and then we're going to take a lone pair on bromine and make a bond to that carbon. And what that gives so bromine will have two lone pairs left, and now both carbons are attached to bromine. And so if you calculate the formal charge on bromine, it's positive 1. So 7 valence minus 2 lines minus 4 dots is plus 1. So you make what's known as a bromonium ion intermediate. So if we, and it showed the stereochemistry here, that bromine would be either setting on top or on bottom of the ring. So that's important to recognize, because then when what happens in the next step, so you lost a Br minus in the first step of the reaction, right? Because that bromine leaves and takes 2 electrons with it. And so what happens in the next step is the other bromine comes in and reacts to open this 3-membered ring up. So as you can imagine, the 3-membered ring is not stable. It's an intermediate, generally meaning it's a real molecule. You could, in theory, isolate it and stick it in the bottle. In some cases, they're stable enough that you can do that. But in this particular case, would not be stable enough that you could do that. So as soon as you make it, it reacts and opens up. But the bromine that comes in has to come in opposite of the bromine that's already there. So you're going to basically end up with the 2 bromines on opposite sides of the ring. So one bromine ends up on bottom, and the other bromine ends up on top. So you could, and so you made 2 cryocarbons in the process. You could have made its enantiomer as well, because you could have had a bromine come in from the bottom, or it could have came in from this side instead. And if you opened it up that way, then that bromine, whoops, so then you would have the original bromine still on top and the bromine that came in just on bottom, and those 2 molecules would be enantiomers of each other. So you make both, but the point is the 2 bromines have to add anti to each other, opposite of each other. So you have to get the trans isomer in this case. So if you had Br2 and an alkene, you had bromine and bromine across the double bond, but you had them opposite of each other. So same would be true for chlorine. So if you added Cl2 to this molecule, and you wanted to clearly illustrate the three-dimensional aspect of it, so we're going to take this and draw it from a side perspective instead. So if one chlorine adds on top, then the other chlorine's got to add on bottom. And are these 2 molecules different? Well, so the other option would have been, so let's draw the other one. So we could have added this chlorine on bottom, and we could have added that chlorine on top. And are those 2 molecules different? And the answer is yes, they are. This is not a meso compound, right? Because the way it's drawn right now, the ethyls reflect and the methyls reflect, but the chlorines don't reflect across a plane. So those 2 molecules are different. They're enantiomers of each other. If we would have started with this alkene, And again, if we illustrate the three-dimensional aspect of this, whoops. So I'm just going to write pH for the benzene ring, so stands for phenyl. And so again, rather than drawing the molecule from that perspective, I'm drawing it from that perspective, so that two things come towards you and two things go away from you. So then we could have added the bromine. So we add bromine and bromine across the double bond opposite of each other. So we could have drawn that. Or we could have drawn that. So are those two molecules different? And the answer is no. Those two molecules are the same because if we rotate around this 180 degrees, so let's take the carbon on the right. If we rotated that 180 degrees, then the CH3 would go behind the page, and the phenyl group would come out of the page, and the bromine would rotate to the bottom. And so we don't do anything to the carbon on the left. And so you can see then if we rotate 180 degrees that there's an internal plane of symmetry there. So this is a meso compound, and meso compounds don't have enantiomers, right? So even though the stereochemistry at these two carbons is opposite and these two carbons are opposite, it's the same molecule because of the internal plane of symmetry. And you can see that if you just take this molecule and flip it over 180 degrees, you can see that the molecule on the top would then match the molecule on the bottom, so it's the same molecule. Same because it's a meso compound. But the point is, in the reactions in this chapter, it's a stereo-specific reaction. You don't get any of the two bromines adding to the same side. The bromines have to add opposite of each other. And so for those reactions that are stereo-specific in this chapter, you need to be able to clearly indicate the stereochemistry of the products. Okay, so another version of this reaction. So if you take CO2 or Br2 and throw in water into the reaction, then what happens? So just like making a bromonium ion intermediate, you will make a chloronium ion intermediate. So take the pi electrons, make a bond of chlorine, that kicks off a chlorine, and take a lone pair on chlorine and make a bond to the carbon. So I'll just add the chlorine to the top, but we could have added it to the bottom. So you get both of those possible stereoisomers. Okay, so you make the intermediate, and so the chlorines on top or on the bottom, but the two carbon-chlorine bonds are not necessarily equal in length. So one of them is longer than the other one. And the one that's longer would be this one. So basically what this does is it opens up the three-membered ring a little bit, and it disperses some of that positive charge to the carbon. And of course it would be better to put positive charge on that carbon on the top than the one on the bottom, because that carbon is more substituted, so it's carbocation-like. And it's better, so that would be a tertiary carbon, right? And this would be a secondary carbon. And it's better to put positive charge density on the tertiary carbon than the secondary carbon. But it's not a true carbocation because chlorine's using one of its lone pairs to make a partial bond there. But this determines the next step in the reaction. The next step is where water is going to go. And water is going to go to the carbon that's got the most positive charge density on it. And so that's going to be the tertiary carbon. So what happens now is a water molecule comes in, attacks that carbon, and opens this chloronium ion, three-membered ring up. And so since this carbon is the one that's carrying most of the positive charge density, that's where the water is going to attack at, rather than the secondary carbon. And so the water's got to come in opposite of the chlorine, so the OH has to end up opposite of the chlorine, so it's an anti-addition, as opposed to a syn addition. So don't confuse anti-Markovnikov with just anti versus syn. Syn means the two things add to the same side. Anti means the two things add to opposite sides. Okay, so water's got to come in from the back, so that's going to flip the methyl to the front. And then the chlorine was on the front to begin with. And then the last step is you lose a hydrogen from the water. And that would be your product. So the OH is back and the chlorine is front. Or you could have the opposite. You could have the chlorine on the back and the OH on the front. And the way that would work is if the chlorine in the very first step happened to come in from the bottom of the alkene, then the OH would have been forced to come in from the top of the alkene. So you would also get the enantiomer. Right, but the main point being is you add H, you add OH and Cl, or it could be Br if you use Br2 in water, anti to each other. And OH goes to more substituted carbon. Right, so this carbon is 3 carbons attached to it. This carbon has 2 carbons attached to it. So we'll just call X bromine or chlorine is going to go there, and OH is going to go there. And they're going to be opposite of each other. Okay, so let me just take one more example of that reaction at the end, just to so if we did that reaction, right, with Br2 and H2O. So let's see, if we call this carbon A and we call this carbon B, so where's the OH going to go? Well, it's going to go to the carbon that's more substituted. So the OH is going to go on this carbon, and the bromine is going to go on that carbon. So you would get the bromine there, and you would get the OH there, right? So in this example, stereochemistry is not as important as it is in this example, because here you can clearly see cis and trans because of the ring. But in this example, that's not important because this carbon has no stereochemistry at all, right? There's no cis or trans possibility, and there's no RNS possibility because it's not a chiral carbon. So in an example like this, it would not be important to illustrate the three-dimensional stereochemistry aspect of it. But it is still happening in anti-addition. You just can't see it in the final product. Okay, so some more reactions of alkenes. So these are, now we're going to shift gears a little bit and talk about oxidation of alkenes. So we don't have to worry about Markovnikov, anti-Markovnikov for these reactions, but some of these we do still have to worry about cis and trans addition. And for most of these reactions, we're not going to look at the mechanisms because the mechanisms are pretty complex. So we'll just say very little about the mechanism. But in some of these, we'll say a little bit about the mechanism. So OSO4 is osmium tetroxide. So if we react that with an alkene, basically what happens, we're going to take the double bond, make a bond to oxygen. 2 electrons are going to go on the osmium, and then we're going to take 2 electrons from here and make a bond to that carbon. And all of this is happening at the same time, so it's going to happen to the same face. So we could be adding the OSO4 to the top or the OSO4 to the bottom. So we'll just illustrate the one adding to the top, but it could have added to the bottom as well. So you make that, what's known as an inorganic ester. So you know what an ester is, right? It's got a carbon-oxygen double bond. Here it's an osmium-oxygen double bond attached to an oxygen with an R group. So this is like an inorganic version of an ester. Okay, so that's what you would get after the first step. So basically we've added oxygen and oxygen across the double bond to the same side. And then in the next step, H2S, and there's a variety of different second steps that you can do. This is just one example. Basically what that's going to do is it's going to decompose this osmate ester. And ultimately what you're going to end up with is 2 alcohols added to the same side of the double bond. So that's basically what you have to remember with this reaction is add OH and OH across the C double bond C, syn to each other. And this is another recipe to do that. So if you take an alkene with cold potassium permanganate, you're going to add the 2 OHs syn to each other. So you could have added them to the top. Or you could have added them to the bottom. Of course, in this example, it doesn't matter because you created a meso compound anyway, so these two are the same. So it doesn't matter if you add them to the top or to the bottom, it's the same molecule. Okay, so for those 2 osmium tetroxide, so that would be the only time you see OSO4 in this in organic 1 or organic 2. So if you see that, you should just know you're adding OH and OH across a double bond, syn to each other. So cold KMNO4 does the same thing. Okay, so if we take an alkene with this reagent, this is what's known as MCPBA. It's an acronym for meta chloro peroxybenzoic acid, MCPBA. So this is a peroxy acid. It's got a C double bond O, 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 H. And so anytime you see a peroxy acid with an alkene, you're just going to make an epoxide. Okay, so we'll go through the mechanism, how this works. So we're going to take the pi electrons, make a bond to oxygen, and we're going to take a lone pair and make a bond to carbon. And these 2 electrons are going to go here to make a carbon-oxygen double bond there. These 2 electrons are going to go there to make a bond to hydrogen. And these 2 electrons are going to go there to make a lone pair on oxygen. So that's what your transition state would look like. So we're making 1, 2, 3, 4, 5, 6, 7. So we're making and breaking 7 bonds at the same time. And then what comes out of that is epoxide. So anytime you see MCPBA in an alkene, just take the double bond, get rid of the double bond, make an epoxide, and you're done. And then the side product that comes out of that is that a carboxylic acid. So metachlorobenzoic acid. Okay, so basically all that we've done in this reaction is we took that oxygen right there and we stuck it right here and made an epoxide out of it. And you can just think of this in terms of the side product, just bump the hydrogen down into its place, and that's the carboxylic acid that you would have. Okay, so you see an alkene, so you may just see the reagent given to you in the name, or you may see the actual reagent drawn out. And in either case, you should just recognize that's going to make an epoxide. So take the alkene and make an epoxide, and you're done. Okay, ozonolysis. So if you take an alkene and react it with ozone. So ozone's a very powerful electrophile. So that's what the Lewis structure of ozone looks like. So we're not going to go through the mechanism of how this reaction works. Just going to teach you how to predict the product. So in terms of predicting the product, it's pretty easy. if you see an alkene and ozone, you're just going to split the double bond in half. So take the double bond, split it in half. Right, and then stick oxygen in, and that's your product. So in this case, you made an aldehyde here, and you made a ketone here, and that's because this side of the double bond had 2 carbons attached to the alkene, and this side of the double bond had a hydrogen attached to the alkene, so that's going to lead to an aldehyde. And so you can see a variety of different second steps. So maybe it's H plus zinc, or maybe it's dimethyl sulfide. These are what's known as reductive workups. As opposed to an oxidative workup, which I'll show you what happens if it's an oxidative workup in a minute. Okay, so that's another example. So if we took this alkene with ozonolysis and a reductive workup. So again, we're just going to take the double bond and we're going to split it in half. So this carbon, of course, has a hydrogen on it. It's just not shown. Okay, so we took the double bond, broke it in half, and now stick oxygen in, and there's your product. So that's the same thing, of course, as 1, 2, 3, 4 CH2s in the middle. 1, 2, 3, 4 CH2s in the middle. So that's the same molecule, right? Just drawn a little bit prettier on the right, but it's easy to see that if you just draw it the way the carbon structure is originally drawn on the left. Okay, so you could do a peroxide workup in step number 2, and this is what's known as an oxidative workup, because peroxide is an oxidizing agent. So there's just a subtle difference in the product. So same basic concept, we're going to split the double bond in half. And then we're going to stick oxygen in. So you have a ketone and an aldehyde. But aldehydes are susceptible to oxidation, so that's the difference. If you would have made an aldehyde, if you use the oxidative workup, you don't get the aldehyde. The aldehyde gets oxidized to a carboxylic acid. So if you made a ketone, nothing happens. But if one or both of the pieces become an aldehyde and you have an oxidative workup, then it's going to oxidize to a carboxylic acid instead. So basically, instead of having an H on the C double bond O, you're going to have an OH there instead. Okay, so if we take this alkene and split it, and stick oxygen in, well, the one on top is a ketone, but the one on bottom is an aldehyde, so that would be oxidized to a carboxylic acid. So that would be the product that you make instead. So you just have to pay attention to your second step in ozonolysis, particularly if the alkene has a hydrogen on it, because if it's a reductive workup, it will stay at the aldehyde. If it's an oxidative workup, then it will be oxidized to a carboxylic acid. So hot CaMnO4 does exactly the same thing as ozonolysis followed by peroxide. So it's going to split the double bond. And if the alkene has a hydrogen on it, then that's going to become a carboxylic acid instead. Okay, so organic chemistry can be difficult for students because you always have to you have to know how to work backwards too. So like if these were your products and you had done an ozonolysis step, what would have been the starting material that you started with? And so this is easy to work through. You just have to recognize these C double bond O's used to be C double bond C's. So those 2 carbons used to be double bonded to each other. So if we work backwards, just take those 2 carbons and double bond them to each other, and whatever's attached to those carbons is still there. So you had a methyl and an ethyl on one, and on the other you had a hydrogen and an isopropyl. So that would have been the alkene that you started with. Or here, so we would need to take these two carbons and double bond them back to each other. Since they're in the same molecule, then that would have been a ring that you started with. So anytime you're making rings in organic chemistry, or in this case you're not making a ring, you're predicting the ring that the product came from. So that would have been a 1, 2, 3, 4, 5 membered ring. So let's draw a 5 membered ring. 1, 2, 3, 4, 5, doesn't matter how you name it. We're just going to put the numbers in there so that we get everything in the right spot. Okay, so carbon number 1 has a methyl group on it. Carbon number 2 has a methyl group. 3 is just a CH2. 4 is a methyl group. Carbon 5 had the OH, but this was a peroxide workup, which means that used to have been a hydrogen. And where's the double bond at? The double bond is between carbon number 1 and 5, right? So you would have started with that alkene, and then you would have made that product if you did the ozone followed by peroxide workup. Okay, so we'll stop there, and the next lecture we'll finish this chapter with a few more reactions of alkenes.